Hello everybody! I hope everyone's having a wonderful day. So today I'm going to be talking and introducing you to the idea of a dictionary, the so-called dictionary problem, and we'll see where this takes us today, okay? So sometimes a dictionary is referred to as a map, which I'll explain why in a little bit. But a dictionary models a searchable collection of so-called records. So these records are, each one is a pair, each with an identifiable key and a value, or we sometimes call this the data of the record. So a dictionary is a dynamic data structure in the sense that records can be added or removed. So we've seen plenty of data structures in this class, and I'm sure you've seen plenty before, all the way from arrays, linked lists, all the way up to ones that we've defined with ADTs, for example, stacks and queues. For example, a stack or a queue, like a stack, I could do pushes and pops. With a queue, I can do NQs and DQs. Notice in those cases, I can add and remove data from our data structures. Well, records are just a little bit more of a complicated structure on top of this. So I have a pair. Each one has a key. So each record has a key and has data, which I'm just referring to as the value here. So the big constraint in a dictionary is that multiple records with the same key is forbidden. You cannot have this happen. All the keys must be unique in a dictionary. So to explain this in a way that's very natural, I'm going to just draw on what some people refer to as a map. So dictionaries are sometimes called maps for this reason. Well, at least this is one of the reasons why some people call them maps. Is that if every single one of your keys is unique, and suppose I have all of these in my collection, I should be able to use the key, and I should be able to look up the record's value. Why should I be able to do this? It's because each one of the keys is unique. If I had two keys that were the exact same, that would mean that I wouldn't be able to tell you which value I should be getting. Should I be getting the value associated with the one record or the one with the other? So it's really natural if you think about it in terms of looking up a result. So that brings me to talking about some motivations behind this. So when you think about a map or dictionary, you could think of it just like a function that takes an input. All the inputs have to be unique so that each one could tell me what the value is for its associated record. So very natural in applications. You'll have it where you may encounter, for example, this manifesting in things like databases, or as even an address book. So for the example of a database, notice that if I wanted to retrieve a certain piece of data that's associated with my record, I have each one of them having a unique key. So in the example of a student record database, one common attribute that all students have is they have student numbers, right? And all of these student numbers are unique. So if ever I wanted to, for example, look up the student information for a particular student, I could use as the key the student number of the student. So I can give the student number and I can try to find the student information. It's quite natural. So you might ask, Dan, why do you call it a dictionary? Well, I like this. It's very natural if you think about it in terms of a book with addresses or phone numbers, a phone book, or a dictionary. So for example, here's a dictionary from the 1940s and 50s. It is an English to Ukrainian translation dictionary. So I have things like this. I'm actually a pretty big fan of history. So for example here, for example, and I know that there's some students that might understand this one. You see a word that's written down on a piece of paper, and maybe you don't understand what that word means. So what do you naturally do? You try to look it up. Well, what you can do with a dictionary, whether it be a physical dictionary like this, or say an online version of a dictionary, is you can use the dictionary, you could find that word in the dictionary, and it will tell you what that word means, whether it be in another language, like in this case, a translation dictionary, or if we're talking about, say, a reference. So this idea of a dictionary applies very much between referencing to something else, given a unique piece of information, just like when we talked about the database example. So for example here, if I wanted to look up the word apple, for example. Why? Because apples are pretty good. Let me find the word apple. So for example, the word apple is jabłko. And any association or context it needs to add, that can be associated with the data here. So I can use apple as the key word here, and the value in this case would be Ukrainian word for apple. So hopefully the idea of a dictionary it's pretty natural. At least I hope that it seems very natural. So let's define what a dictionary is, everybody. So I'm going to define the ADT for a dictionary. Now, one thing that's very important for you to know, just contextually speaking, is we're going to talk a lot about how we can implement dictionaries. So as this course is going to progress now, I'm going to focus on the dictionary ADT, and we're going to talk about different ways we can implement dictionaries, and we'll use it as a motivation to develop and discover or explore more data structures. Why? Because it's one of the fundamental data structures. So the so-called dictionary problem is the question of how can you most efficiently implement all of the operations of a dictionary. So as we may see, and you may get a very natural intuition with this based on how we talked about linked lists, arrays, or even lists, there might be trade-offs between certain operations depending on how we structure the data and how we design the algorithms. So just keep that in mind. So that's going to be a theme that's going to permeate the remainder of this course. So it's going to spread itself out like a piece of butter all across a long piece of bread. So what's a dictionary? A dictionary, D, is a set of records, each with a key and value or data. I'll use value and data as synonyms. And it supports the following operations. These all seem rather natural based on what I described over here. So these are going to be the main three I'm going to focus on. There's other operations as well. But the first one is called get. So I give you a key. And I want to know if D has a record with key K, return the associated value for that given key. So remember, just like I said over here, I imagine I give you the key. I want to find it, and I want to return what the value is. Seems very natural, right? So that's what the get operation is. Now, if it does not exist in the dictionary, you're going to return null. So this is how we're going to define the dictionary. Next is the put operation. Some people call this insert. So the idea is that I have two parameters or two inputs. I have key and a value. So using key and value, I'm going to insert a record with this as a pair. So keep in mind it can be given as the pair itself, or it might be the two separate attributes. Then you create the record inside the data structure when you're implementing it. It doesn't matter in the specifications we have here. So you're going to insert the record KV into D if no other record with key K exists. If that is the case, where there's already a record with key K in it, you're going to return an error. Now you might ask, Dan, what does it mean to return an error? So what does that mean? So what does this mean? So I must stress that if this isn't really something your language can sufficiently provide you, you can always return null, for example. That'll be clear enough to indicate to somebody that, hey, look, there is no record with, like, you can't do this. It will override information that already exists in the dictionary. Now, the convention that we're going to adopt is that you're not allowed to overwrite the information that's already there by inserting in a new record that overwrites the old one. Instead, we're going to make it so it throws an exception. So in C++, what I'm talking about is throwing an exception. So this is one way of facilitating the returning of an error. So I put some links in the notes for you to check out if you're curious about those. We will see how we can use exceptions on one of the next assignments. And you also will see it in the lab too. In fact, I have a link to something from the labs that I want you to take a look at that gives you some context of how an exception works. So you'll get some experience trying that out. So that's what put is. So now if it does not, so keep in mind, if there is no duplicate key, that's possible in this case, then you just insert it in. So you just insert the record into D, and that's it. But if there's a duplicate, remember, you're going to report an error. So that's what put is, remove. What we're going to do here is I'm going to try to ensure that if I attempt to remove something, it better be in the dictionary, right? So you must note here that when I do this remove, and also I do this put operation, you're going to find in some of the data structures that we're going to see that determining if the information is there already is going to play a very important role. So I want you to just take note of that. So when I do a remove, if there is a record O with key K, you're going to remove O from D and return its value. So quite similar to when I had my implementations of, say, a stack where I want to pop, I want to get back the element that I have here. In this case, what we're interested in is the value of the record. Now, if I fail to find it, so if there is no record O with key K, then I'm going to return an error. So this is the same thing. You're going to throw an exception. So, or at least that's one way we could do it in a programming language just like C++. Now there's two other operations. These are rather straightforward operations. One is called size. You just return the number of records in the dictionary and is empty. Sorry, I'm getting very excited here. It returns false if there's at least one record. If the dictionary has no records, then you return true. It's quite natural, So there's other optional operations you may also have in a dictionary. I'm going to talk briefly about those. So let's head over here and talk a little bit about that. But yeah, this is the idea of a dictionary. It's very intuitive. Is that I have keys, and I'm interested in the data that's stored with each one of the keys in a record. And I must stress that dictionaries are fairly general data structures. If, for example, you're not very interested in the value data part and you just want to care about the keys, you can use this in many other settings too. Just the only constraint we have here, but it's not necessarily a constraint on the data structures we use to implement them, is that the keys are unique, which in many settings you can set up a configuration like this without ever having to really worry about the data attribute. Many of the data structures we're going to see have this feature. So I'm going to talk briefly about some optional operations. I'm not going to focus so much on these. Talk more about those types of things in the lab. So some optional operations using iterators, which I'll make a mention about in a moment, include the following. So here's 3 different other operations you can use that are based on iterators, which I'll explain what those are in a moment. So I'm not going to focus much on talking about iterators themselves. I want to tell you what the idea of them are, and if you're curious about them, you will see them eventually if you have not seen them before. So there's 3 other functions you can have, is entry set, key set, and values. So this will return, so entry set returns an iterable collection of the records. And some people call records entries of the records of D. So this one will give you some way to traverse or iterate over all of the records in D. Key set, it does something quite similar to the same thing. It returns an iterable collection of the keys of records in D. So this one will provide you some mechanism to traverse through all of the keys of records in the dictionary. This one is going to be the exact same thing, So values is going to be the exact same setup, except it's going to be values of records in D. So I just want to make a remark about iterators, because I'm not sure if you've seen them before. I know that you will see and play around with these in the lab. You'll get to see some examples of these in the lab. So don't worry. I've also provided you a couple of links you can check out to learn a little bit more about iterators. But I'm not going to focus so much on them here. So just to be very clear, what's an iterator? So if you've never heard of what an iterator is, it provides the functionality of iterate, so to iterate or traversing over the elements in a data structure or collection. So in many programming languages, or specifically object-oriented programming languages, it's very common, is the concept of an iterator. So I must stress just a couple of ideas, just to give you the flavor for how iterators work. So under the hood, iterators are essentially built around pointers. But I think it's best to just talk about some examples of how you're familiar with traversing or exploring over a data structure. So for example, if I give you an array, so let's talk about an array and a linked list. So when we talk about an array or a linked list, a very natural question is, how do I traverse over all the elements in the array? And if I have a linked list, how can I traverse through all the elements in the linked list? Now I must stress that I could also do this, the same idea with also a doubly linked list. Say if I wanted to start it at the back, and the tail of the linked list all the way to the front. You can define iterators so that they can go from the beginning of the data structures or collection all the way to the end, or from the end to the front, depending on how the data structure is implemented. But I want to really hammer in an idea about iterators. So when I traverse through an array, we use a very standard pattern, right? What we do is we have it where we have positions, right, in our array. Say if I have n elements, it indexes from 0 to n minus 1. And if I want to access each one of the elements, what would I use? Well, what could I use? Well, I could use a for loop, for example, or a while loop. Well, a for loop is very natural because I know how many elements there are in my array, or how many elements I would like to explore. And I could just simply have a for loop, right? I have it where for I is assigned 0, I is less than n, I plus plus, and then you can index each one of these one after the other using by indexing them directly using square notation, right? So for example, if this array was called capital A, if I want to access A sub I for any one position, I can use a for loop to access each one of them, right? Because I can index each one directly, right? But notice the idea as I go through here with a for loop. Well, what about here with a linked list? Well, remember, the linked list isn't just simply this. It's also that it has the head of the linked list. So how did we do it where we want to traverse through the entire linked list? Well, I created a current variable that's going to point at whatever head is. So say if I have current here. So I copy over whatever the address is. Where I can figure out where the head of the linked list is. And then I just simply have a while loop, right? I could ask while current is not equal to null, and I could go through each one of these nodes, and I could figure out what each piece of data is in the linked list, right? Notice that these are both fairly straightforward ways to explore these two data structures. But notice that there's something that's quite common in between them, is that I start at the beginning, and then I simply get the next element every single time. And then there's some stopping condition for doing so. And this is true for both of these, right? I know when I'm not supposed to index any further, right? I know if I try indexing, say, a sub n, that doesn't exist in this array, right? Just over here, I know when the pointer that I have is going to be pointing at null for the next node, right? So you could think of an iterator as a way to facilitate or abstract away. So I'll say iterators facilitate abstracting away the perhaps more specialized method of traversing the data structure. Because in these cases, in these two cases here, you know how to do both of these. And you'll say, okay, Dan, why do I need this iterator? In fact, you don't need them. It just makes things easier from more of an object-oriented standpoint. So suppose I didn't have an array or a linked list, something more complicated. Say, for example, my dictionaries. So if I have a dictionary that supports these operations and I wanted to get all the records, I want to go through and I want to be able to get each one of the next records in the dictionary until I've examined all of them. Or suppose I want to go through some and do some modification. Now, I may not necessarily know how the dictionary is actually implemented under the hood. What I would care about, if you look at my dictionary definition, I look at it as an interface, I would just like to be able to get an iterator so that I should be able to get each element, get next element for every single one of them, or in this case, each record. I want to be able to get each record, no different than the ways I knew how to. So this is fundamentally based on the same idea. Suppose I start at a beginning. So I start at the beginning and I want to get the next element each time. I want to have some stopping condition for me to stop doing this to know that I have traversed through all the elements. So iterators provide a general plan for how to do this. And it's based simply on the idea of I like to think of it like a zipper, is that it will start you at the spot where the first element is. And every time you perform the next operation, it will set you up pointing at the next record or element or part of the data structure you're looking at. And I like to think of it like a zipper, is that the iterator will have some code in there that's going to get you to the next element every single time. Like if I'm zipping up a jacket, and suppose this jacket is really old and the zipper jams if I push it down. So if I start this up, it'll start me off, say for example, right here, or perhaps right here. And every time I get the next element, it'll take me to the next one and I can examine that element without ever having to know what's going on underneath the hood. So quite simply, you know how to do it with an array, you know how to do it with a linked list, but what if I gave you a general way to do it without knowing what if it was a linked list or an array? That's the purpose of an iterators. Iterators are used very often if you have, say, an interface like the one I have defined for my dictionary, and each one of my implementations could have a different iterator for that specific implementation of the data structure, for which every time I want to go, for example, through a for loop and I want to go through each one of the elements, I have some way to go through each one without knowing how I'm actually going through each one of them, whether it be look like this, could look like that. It could, for example, later on we're going to talk about trees, it might look like a tree. But in the notes, I'm going to provide a couple of links. If you're curious about learning more about iterators, you're going to see them at some point in the lab. So I just want to give you a flavor for this. So iterators are this wonderful idea that abstracts away the pattern of exploring or traversing over elements in a data structure. I like to think of it like a zipper. So I need to acknowledge this because I don't know if you've seen this idea before, and I just wanted to introduce you to the idea. It's a neat idea. But remember, the point here is not that, oh yeah, I know how to do this, I know how to do that. I could easily just implement these. Correct. That's perfectly fine. But the idea is that the iterator provides you a way to abstract away knowing whether it's an array, a linked list, a tree, or some other implementation under the hood. You just want to care about accessing all the elements without having to know how it's actually implemented, because that might be more specialized than you're prepared to do. If you hand over your code to a user, they don't want to necessarily know a sophisticated algorithm to access all the elements. You're giving them a very simple way to traverse through all the elements where you hide away how it's examining and getting the next element each time by giving you a pointer to where it is so you could dereference it, for example. But yeah, so that's the idea of an iterator. I wanted to just make a remark of this. These are typically considered optional in a dictionary, so we're not going to focus on these ones. So I want to give some examples of playing around with the dictionary data structure, well, the dictionary ADT, so that we have a flavor for how these operations work. So let me just... Let's do just a few of these. I have a whole table full of these. I'm just going to do some of this. So I'm going to make a table. I'll use operation. So I'll tell you what the operation is. So I'm going to start off with an empty dictionary. So I'm going to try out each operation. It's going to output something. So this will be what it will return at each one of the operations, and then I'll tell you what the state of the dictionary is. So suppose I start off first with an empty dictionary. So I'm just going to mention that here. So we're going to start with an empty dictionary, meaning it has no records in it. So first I'm going to try is empty. So if I had a dictionary called a D, for example, this is me going D.isEmpty, or if I had a dynamically allocated, I would go D arrow is empty. But keep in mind in this, when we talk about these things at a higher level, I'll just normally use the dot notation, unless it's very important. But I expect at this stage you'll be familiar with the difference between that. So is empty. So if I call is empty on my dictionary, in this case it'll be true because the dictionary is empty. Now suppose I wanted to put in a record with key 5 and its data is A. Now put doesn't return in this sense because notice that I don't have any records right now, so it's not going to return anything in terms of an error or anything. It's just going to put this right into here. So I'm going to put a new so I put my record in with 5 and A, like this. I could put another record in. Suppose I have one with key 9 and its data is B. This isn't going to output anything. So I have 5 and A, and I have 9 and B. Now I must stress that the order I'm writing this in doesn't matter. As far as we're concerned, these are just part of my set of records. Now, if you implement it a very specific way, the ordering of these might be different. But we don't care about that at this stage. We're just talking about the ADT. So if I give you 3 and I try to put in C, notice that I'm not going to output anything because I'm just going to insert this right into the dictionary. So I have 5A, then I have 9B, and then I have 3C. Let's try another one. Let's put in 7D. Notice so far I haven't I tried to insert a record with a duplicate key yet, so I'm just putting in some records into my dictionary. So I have 5A, 9B, 3C, 7D. Okay, so now let's try now let's do this operation. Let's try putting in 3 with data E. So do I run into any issues by doing this? Try to put in a record with key 3 and its data is E. So the unfortunate thing is that we cannot put in a record with this pair at all. It's not because this is an E here. Keep in mind, it doesn't matter if there was another E in here. What matters here is that I already put in a record with 3. So here I would get an error. So in this case, you might report back and tell me what was the data in the record at that time. So in this case, here's C. So I'm going to just tell you that, oh yeah, C already has that key. So I'm not going to modify it. So instead, I'm just going to leave it alone because I report back the error. I'm not going to overwrite the data that's already there. So keep in mind the convention. Some people will allow it to overwrite. We will not allow that to happen. 9B, 3C, and 7D. So if I attempt to get, let's try using the get operation. So if I try to get 9, notice that 9 is sitting right here, right? It has data, its value or data is B. And nothing has changed. If I attempt to get 2, so if I attempt to get 2, notice that I have no record with a key 2. So in this case, it will return null. Nothing's changed. If I attempt to get the size, let's try getting the size of our dictionary. So far, I have only 4 records in here. So it will get 4. And let's try removing, let's do a remove operation. Let's try removing 5. So if I remove 5, it's supposed to return back to me the data or value of that record if it exists. If it doesn't exist, you report an error. So in this case, 5 does exist. There's a key with 5, so I return A. And whatever's left in here will be 9B, 3C, and 7D. So these are some examples of me using some of the operations here, just to give you a flavor for how the dictionary works. So I haven't told you anything about implementing the dictionary, but this should give you a flavor for how it works based on our ADT. So now that I've talked about what a dictionary is, we did some examples. I talked a little bit about some technical aspects of some of these operations. Let's talk about an implementation of the dictionary. We'll talk about 2. So let's head over here. We're going to talk about a couple of different implementations for our dictionary. So I'm going to go a little bit faster because we're familiar with a lot of these ideas. Okay. So let's talk about some simple implementations. So we're going to focus on get, put, and remove. Most of these implementations, determining the size is very commonly associated by just having an attribute that keeps track of how many elements there are. Just like when we see in our link stack or link queue implementations, I can actually just store that as an attribute if I'd like. So let's talk about some simple implementations. So how can we implement a dictionary? So we're going to I just want to touch upon this because I want to show you using the current things that we've seen so far, what we were capable of. So that when we move on to our next subjects, our next topics, I'll be able to give you more ways you can tackle these using some of the ideas we've seen or possibly new ideas. Let's talk about some simple implementations here. So the first one I'm going to talk about is, so we're going to implement as an unsorted list. So we talked briefly about lists. Unsorted list using a linked list. So we're just going to use a linked list to maintain an unsorted list. So all we're going to do is adapt the ideas that we know about for linked lists. So it's going to be rather straightforward. So let me just write down what the operations are. So if we consider get, what we're going to do is we're going to just traverse the linked list in the exact same way I talked about earlier when we were talking about iterators. I start at the head of the linked list and I make my way going through each successive node. I examine what is the data. I examine what the record is because each one of these nodes is going to have as its data the record. So I'll show you in a picture in a moment. Just traverse the linked list. If a node contains a record with key K, return its value. If the entire list is traversed, return null. So it's very natural to just be written out like a while loop. So you'll just have a while loop. You examine what the key is for each one of the data components or data attributes of your nodes. You just examine that. And you see if that key is there. And if it is there, then you return the value of the record that's stored at that node. So next we have put. First, what we do is first check for duplicates. So you can just simply use get, for example, to accomplish this. You can use get, or you could just traverse through the linked list again. Either one's fine. It'll give you the sufficient information to determine if there's duplicates. So just traverse the list to check for duplicates. And I'll just say, example, use get, and then we'll return error. If a duplicate is found. If a duplicate is found, and if no duplicate is found, just create a node with the record. And insert it at the front of the list. So you don't have to go through the entire list to find where you should put it. You can just put it at the front or the head of the linked list. It doesn't matter, we're just maintaining an unsorted list here. So let's consider remove. So you just simply, so first you need to see if the record exists, right? So again, you can always just simply traverse through the linked list to see if it exists, see if the record exists with key K. So you can use the same idea I talked about earlier here. However, you'll notice that I still want to remove the record, so I'm just going to describe it this way. Traverse through the list. Remove the node. Remove the node with key K if found. And return its value. If the key is not found, report error. So you might ask, Dan, what does this look like? So I just want to give you a flavor for how this is, and you know how a linked list operates. So just going to draw a picture first. So let's head over here. I'm going to draw a fun picture. So I'm just going to have a linked list, just as I described. So I just have a linked list like this. So I have the head of the linked list. So I just have a linked list where each node is going to store a record as its data. So each one of these will have, you'll be pointing to some record. So for example, if I have 7D, this would be the key, and this is the value. So you have 3 and C. I can have 9 and B. And I have 5 and A. Now, what the records of the dictionary are these. So these are all the records. And what's happening is at each one of the nodes, you store the record. So notice that our implementation description here for doing an unsorted list is very natural. So what you would do, for example, with get, like I said, you'll just traverse through the linked list, one after the other, and you'll check its key. Each time I'm at a node, I check its key, and I see, is this the key I'm looking for? If it is, then I'm going to take it, return back its value, or data, whatever you'd like to call it. It's a little bit confusing if I call it data here in this context, because technically this is a data attribute for the node. So likewise, if I want to do a put operation, I have to check for duplicates. So I first scan through here to make sure there's no record with the same key K. If there is no duplicate, then I just insert it at the front, just like you're doing when you talked about, remember we talked about like our link stack, for example, where you insert at the front of the linked list? Do the exact same thing here. Once you know there's no duplicates. And then of course the remove, you check to make sure that the key exists. So if the key exists in the linked list, you're just going to perform a deletion at that point in the linked list. So for example, if I wanted to remove a record with key 9, I would remove this node from the linked list, meaning that I would have to get rid of this. So I would return, so remember, I return the data of the record, then I delete the node afterwards, and I make sure I have the rest of my linked list maintained, right? And that's all it is. That's all it is. So this is an unsorted list implementation using a linked list. So what's the time complexity here? So let's talk about worst case time complexity. So let's talk about these. So worst case time complexity in each one of these cases. So remember put to do, actually let's talk about put first. So put takes, now remember, before I can perform the insertion, I have to make sure there's no duplicates, right? Meaning there's really two things I have to be careful of. It's because the algorithm has to check for duplicate keys. In this case, it doesn't matter. There's no cap on how many nodes I'm allowed to have here in our assumptions here. As long as I know there's no duplicates, we know that this takes big O of n time. If n is the number of nodes in my linked list or the number of elements in the dictionary. So we need to check for duplicates, right? So it's from that check that we have to do. Now, remove and get. Now, remove and get, these both take big O of n time as well. Now, think about it. From the worst case scenario, to do a get operation requires me to traverse through the entire linked list, right? To do a removal, in the worst case, in both cases, it may be the case that the record doesn't exist, right? as in the worst case, this is when the record is not found. The record is not found. And I'll say this, just traversing the entire list. So a very natural question comes out of this. Very natural question is, can you do any better if I were to sort the information here? So a question for you, very natural one. Notice that I maintained an unsorted list with my linked list. What if I changed it from an unsorted list to a sorted list? Could I improve what I've currently done here? So suppose that the linked list is being maintained where it's being maintained so that all of the record's keys are from smallest to largest in this linked list. Now remember, a linked list is not like an array in the sense that I can just easily just access any point in the linked list, right? So can we improve any of these worst case time complexities? The answer is unfortunately no, we can't. At least in the sense of our setup here. So notice that if I were to give you a sorted linked list, a sorted list implemented as a linked list, notice that if I were to try, because keep in mind, remove and get aren't going to get any faster, right? Because remember, I still have to, if in the worst case, the record may not even be there, right? So I still have to go through the linked list anyways. It's really this, if we can make this be faster. But notice that the check for duplicates, the advantage we have when it's sorted is that I don't necessarily have to explore the entire linked list. I can just stop wherever is necessary. So keeping my finger, I can look at, for example, if I started with 3, then I go to 5, then 7, then 9. Say if I'm looking to insert a record with key 6, I don't have to go past the key. When I hit key 7, you know that we're okay. I don't have to go any further. However, we can't do any better because imagine if I gave you I try to do a put operation and say the key that I'm trying to insert in is larger than all the other keys, which would mean I have to traverse the linked list anyways. So you can't, using a sorted list implemented as a linked list doesn't make you any better. You're still going to get these. This is true even with a sorted list instead of an unsorted list, because you'll notice I just use an unsorted list here. So it has its advantages, but from a complexity standpoint, it doesn't make any difference. So a very natural question is, you'll notice that if it's sorted, it didn't matter with my linked list, right? However, it would matter if I could actually index into the positions knowing that the collection is sorted already. So if I can index any one position, just like an array, that might change. So let's talk about that. So that's another way I can implement the dictionary, is I could use a sorted array. So let's talk about a sorted array. What about a sorted array? Well, in a sorted array, if I wanted to do a remove operation, or if I wanted to do the search, these don't seem to make much of a difference, right? There's two reasons why, right? The first one is that this is still true. This is just as true otherwise, right? It may be the case that the record is not found. But here's the neat thing about having a sorted array. So remember, ultimately I still have to, if I have a sorted array, if I'm trying to get I can just use something else, right? So my get operation, so if I use get, we can use binary search, right? And we know how to do that in big O of log n time, or log base 2 of n. So we can speed up the get operation. So if ever we want to get, we can always use binary search, which speeds up this. Now, the reason why I bring this up is because at some point we're going to see a data structure that I'm hoping to motivate how we could speed up the operations of insertions. And my hope is that I'm going to be able to convince you at some point near the end of this course that we're going to see more data structures that we can actually achieve these kind of running times instead of linear time. So that's one advantage we can get from the sorted array. So keep in mind that if I use an array, however, the major drawback is that if I tried to do insertions, I might have an array that becomes full. By the same justifications I talked about, when an array becomes full, I may have to resize the array before I can insert the record in. So that will require me to use a linear number of operations as opposed to just simply trying to seek it out, right? Because remember, I could first have to figure out if it's in there first. Then the other thing, because remember, when I have an array, I can still use binary search to find it, right? So I can use that to find it. So I can find a record here. But when I do put or remove, I still ultimately have to do something. I have to create a new record. But if I don't find it in here, I have to put it somewhere, right? Which means I'm going to have to put this new record in here. Then I'm going to have to shuffle over a whole bunch of elements this way, right? But how many shuffles can happen at most? Well, it could be something that's linear in n. So it's going to be n, right? So it's going to be big O of n in the worst case in this scenario. That's true in put and remove. The same idea applies here as well. Is that when I do a removal, suppose I do find the record I want, I'm going to have to get rid of this, meaning I'm going to have to shuffle all of these elements to maintain the sorted order of these, because I don't want to have gaps at all in my array. I have to fill in all the spots where I'm going to remove an element. Otherwise, it's going to be rather difficult to be using binary search to find anything. So in those cases, when I have the sorted array, I still get, for put and remove, in the worst case, we still are big O of n, worst case. Worst case time. So anyways, with that being said, we're going to stop right here. I was hoping this was going to be a little bit shorter, but I wanted to make sure I took a little bit of time to digest this with you so we could talk a bit more about different ways we could implement dictionaries. So when we come back, I'm going to show you an interesting phenomenon that we can make use of by using space to help us accelerate or speed up operations. So-called hashing. We're going to use so-called hashing, and we're going to make some statistical assumptions to try to speed up some of these operations on average. So we're going to see how that plays out in the coming couple lectures. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.